Okay, good morning. Okay, this is Professor David J. Delos Reyes. My topic for this morning will be a continuation of my subject matter AC machines, and I am now on lesson number 63, AC machines. And the title of the topic will be Alternator Armature Circuit Parameters. How do we determine the parameters of an alternator? Parameters meaning the resistance, reactance, and impedance. Because in the so-called computation of the voltage regulation, we must have to compute for the IR drop of the armature and the impedance drop of the armature. The subject matter for this morning is actually a complicated one, theoretically speaking. But since our subject matter concentrate more on the so-called calculation, I will try to summarize the concepts regarding the determination of the parameters of an alternator. Okay, let's proceed. The subject matter for this morning will be continuation of my subject matter AC machines. I am now on lesson number 63, and the title of the topic is actually Alternator Armature Circuit Parameters. We are done with the transformer. When we were in the topic transformer, we also computed the so-called voltage regulation of the transformer. Will it be stable enough to, what you call this, deliver a voltage to our houses? Like the same in the alternator, there is also the so-called voltage regulation. Will an alternator generate a stable voltage for us to use it in our houses? Okay, let's continue. To bring out the so-called the concentration of the subject matter is not on the theory side. We discuss a little bit on the theory side, but the concentration is actually on how to bring out the armature resistance, reactance, and impedance, and the computation of the so-called voltage regulation. Because voltage regulation is actually the voltage at no load minus the voltage at full load over voltage at full load times 100%. And the voltage at no load, okay, it is actually greater than the voltage at full load by the value, okay, designated by the armature drop and the reactance drop. So the concentration of the subject matter for tonight will be in the computation of the IR drop, okay, and the IX drop. There should be an I over here. Because this is a vector diagram for the IR drops and the computation of the voltage per phase at hub. Oh, they should be no load. Oh, they should be, we should interchange this one. This is full load, and this is no load. Right? This is also multiplied by a current I times X of S. So the concentration of the subject matter for this morning will be in the computation of this IR drop and IX drop, and to compute for this voltage drops here, okay, we must have to determine the circuit parameters of the alternator. And actually, the way how we engineers do it is actually by performing the open circuit voltage test and the short circuit test. Oh, this is now just a summary. If you try to read our book, it's a complicated thing, but this will now be the summary. Okay, let's proceed. Considering for the meantime that the alternator is actually connected, Y connection, Y. Okay, this is one phase, it's three phase, right? And we must have to compute for RDC over here. If we try to compute for this voltage drop over here, we must have to determine the voltage R with the subscript DC here, meaning resistance, direct current value. Okay? The resistance that is needed in the computation of this IRS is not actually RDC, it's actually RAC. And there is a certain constant K times RDC. So if we could determine RDC here, okay, we could compute for RAC by multiplying by a certain factor K. And according to the formula I placed here, the relationship of the AC resistance, alternating current, and resistance direct current, there is a relation. Okay? It is designated by this formula. And for alternators, the range of the value K is actually ranges from a value 1.25 to 1.5, meaning the AC resistance is greater by a factor equivalent to 1.25 to 1.5 compared to the so-called DC resistance. So on the safe side, if we try to compute for this voltage drop here in the computation of the voltage regulation, we will be using this formula here for the resistance. Okay? This resistance over here, RS, is RAC. It should be given by the formula 1.5 for RDC using the average value. Because there is a range for the value of K, it is 1.25 to 1.5, but the usual thing that engineers are using in the computation of RAC is actually 1.5. So in the computation of this RS here, okay, we use this formula, it's 1.5 times the DC resistance measured across this. It should be the voltage per phase value, because what we could measure here is the line-to-line resistance. It's the resistance of the first phase and the second phase. So if we try to get the resistance per phase, whatever reading that will be measured over here, we divide it by 2. So this is RDC over 2. Okay, the resistance per phase. So actually, this value here is actually the resistance per phase. Okay, so we eliminated one problem in the so-called computation of the voltage regulation, because we now know the AC resistance. If we could measure RDC over here, we divide it by 2, so we could determine the DC resistance per phase. Right? It's balanced. So upon taking the value of RDC over 2, we multiply that by 1.5, and that will be R sub is now here. Okay. We concentrate more on the formula side, and at least we know how we determine RAC from the reading. Okay. What's next? We'll compute for the so-called Z, capital letter Z with the subscript S, meaning S refers to synchronous impedance. And if you try to Google what's the meaning of synchronous impedance, it's a complicated thing. Synchronous emanates from the word, because alternators, before they will try to generate voltage feeding our transmission lines or grid lines, okay, the speed of the alternator should be equivalent to the speed of the so-called prime mover. Okay, because there is a prime mover for the alternator. Like in the hydro thing, that synchronous speed should be the synchronous speed of the turbine driving the alternator, right? So there is a term here, synchronous impedance. So if we now try to compute for the impedance, okay, synchronous impedance per phase, it should be capital letter E per phase over I, capital letter I with the subscript SC, meaning short circuit current. We must have to determine the value of this one here. This is actually the open circuit voltage per phase. Okay, open circuit voltage per phase. Open circuit meaning the alternator is running, no load. Okay, so if you could determine the line-to-line voltage, right? And if the connection is a star, you divide that line-to-line voltage by a factor of square root of 3, we could compute for the open circuit voltage per phase. This value here. So if we are given the line-to-line voltage at open circuit, you divide it by a factor of square root of 3, and that will be the open circuit voltage in the computation of the synchronous impedance. How about ISC? This short circuit current is actually very critical because for us to compute for this, the voltage, open circuit voltage per phase should be divided by the short circuit current. And where do we get the short circuit value? It will emanate from the so-called short circuit test. Right? That's why there is the so-called open circuit test and short circuit test. For the short circuit test, it is something like this. If we try to consider for the meantime, because the short circuit test is actually a graph of the short circuit current as abscissa, ordinate. And the abscissa is actually the value of IF, the excitation current. Okay, let's erase this voltage per phase. And let's try to consider for the meantime the straight line graph. The straight line graph is actually termed to as the short circuit test. Okay? This is where we get the value I short circuit. Okay? Engineers used to graph the relationship of the short circuit current and the field excitation current. And the graph of this is actually what they call this a straight line. It's not a curve, it's a straight line. So this is a straight line. It seems we are an analytic geometry. And if we try to take the equation of this, it should be the short circuit current as a function of I sub F. I sub F is the excitation current. What's the use of the excitation current? Excitation current is the current that what you call this produce the magnetic flux that will be cut by the conductors as it rotates, okay, to generate voltage. So this graph here, considering for the meantime the straight line, because the curved line is actually the open circuit test. If we try to graph short circuit current and the field current, the graph is this, okay? And considering this point, just consider this point for the meantime. This portion here is the short circuit current, okay? And this portion here is the excitation current to produce that short circuit current, okay? So whatever coming from the intersection, if this is IF, it intersects the short circuit test, and if we try to draw a horizontal line, that horizontal line is actually the short circuit current. And the short circuit current here is the one that will be needed here. Okay? So whatever short circuit current coming from the short circuit test line, that will be the one that will be used in the computation of the synchronous impedance. Okay? So the ratio of the open circuit voltage per phase all over the short circuit current emanating from the short circuit test diagram, okay, the ratio, this is termed to as the so-called synchronous impedance, and the unit of this is actually in ohms. Okay, so we have determined already the two parameters needed in the computation of the so-called voltage regulation. We now know the value of RAC. It is 1.5 times RDC. And for the impedance, the total impedance, this one. The total impedance value of the alternator should be the open circuit voltage per phase all over the value of the short circuit current emanating from the short circuit test diagram. Okay? So the short circuit test diagram is actually very important. If you try to move your field current here, a little bit to the left. Supposing we go to this line. Okay, this should be the value of I sub F. At this I sub F, there should be a corresponding short circuit current. Right? If you try to plot a graph IF here, there is a corresponding short circuit current for that one. And that's how we get the value of the synchronous impedance. Okay? We are now on the last part of the computation of the voltage regulation. How do we compute for X of S now? Oh, that's an easy one now. Because we pass by the subject matter AC circuit. Right? Under the standard AC circuit, a combination of R sub S plus Jx sub S is actually Z sub S. Synchronous impedance is actually the value of a synchronous resistance vectorially plus J synchronous reactance. So if we know the synchronous impedance, we now know the so-called synchronous resistance. We could compute for this by using Pythagoras principle. Okay, the square of Rs, just taking absolute value for the meantime, the square of Rs quantity square plus the value of X sub S quantity square should be equal to C sub S quantity square. So if we know C sub S and we know R sub S, we could compute for I sub X sub S. It is given by this formula here. And the unit of this is ohms, and the proper term for this one, it should be synchronous reactance. X refers to reactance and the subscript S refers to synchronous. That synchronous thing emanates from synchronous. If whatever the speed of the prime mover, it should be equivalent to the speed of the alternator. That's why we term to as synchronous. Right? So we now know X of S. Okay? So in the computation of the no load voltage per phase of the alternator, so we could determine the percent voltage regulation, the one we computed from the last topic. Okay? This diagram refers only to unity power factor, because if the power factor is lagging or if the power factor is leading, the vector diagram will be different. So just to simplify the vector diagram for illustration for this morning, I just give you a vector diagram for unity power factor. It is something like this. The voltage per phase is at 0. And the current is also at 0. So at unity power factor, the voltage per phase and the current are actually in phase. If this is the voltage, this is the current, they are in phase. It is this. Okay? Then to compute for the voltage per phase at no load, we must have to take the product of the short circuit current times R sub S, the one given by this formula. And again, we will take the product of the short circuit current multiplied by X sub S. This is X sub S was actually computed by using this. And before we could compute for X sub S, we compute for Z sub S, okay, by using this formula. Voltage, open circuit voltage per phase divided by the short circuit current. And this short circuit current emanates from the so-called short circuit test diagram. Okay. For repelled excitation during the test, there is a corresponding short circuit current for that one. Okay. So we take this value here, we place it here to compute for the value of C sub A. So if we could find the product of I times R sub S plus I times X sub S, we could compute now for the voltage per phase with the subscript no load. Okay, again, we use Pythagoras principle. Okay, I will try to erase this one. This should be I will just write the equation on how to compute for the voltage per phase at no load. It will be voltage per phase at full load plus I times R sub S quantity square plus I times X sub S quantity square. Then we'll try to take the square root. Right? Because this is a right triangle. This is the hypotenuse. This is the opposite side, and this is now the adjacent side. The adjacent side is comprises of two values, the voltage per phase at full load plus the product of I times R sub S. They are both real. This is imaginary. Okay? So to compute for this, it will be the square of this plus the sum of the square of this, then take the square root. So if we try to compute for the percent voltage regulation, that will be an easy one now. Am I still on camera? It should be the voltage at no load minus the voltage at full load over the voltage at full load times 100%. Okay? This is given, we computed for this, so we could compute for the percent voltage. Okay, that's it guys. That's how we determine the percent voltage regulation by using the parameters of an alternator. And to determine the parameters of an alternator, we brought out the open circuit test and the so-called short circuit test. Okay? For the open circuit test, it's actually a graph of the field excitation current and the open circuit voltage per phase. If you try to excite that alternator at a certain I sub L, if you try to draw a vertical line, it intersects the open circuit test curve. And again, there should be corresponding, what you call this, horizontal line emanating from this intersection here. And this voltage per phase, okay? And this voltage per phase, okay, is actually this one. Okay? The one on the numerator. So it is important that we perform the open circuit test and the short circuit test in the computation of the synchronous impedance. This voltage per phase emanates from the open circuit test, it is this, and this short circuit current emanates from the short circuit test, okay, and it emanates from this graph, the straight line. Actually, this is now a combination of the short circuit and open circuit test. Okay. For the short circuit test, it's just that the ordinate is the short circuit current, the abscissa is I sub F. Okay. And for the open circuit test, it's a combination of the abscissa is still the excitation current, and the ordinate is the open circuit voltage per phase. So this voltage per phase emanates from the open circuit test diagram. The short circuit current emanates from the short circuit test diagram. Okay? We now know R sub S. We now know C sub S. We could compute for X sub S. Okay? So if we know the short circuit current, we'll just multiply that by the value Rs and X sub S. The Newton's Pythagoras principle, we could compute for the no load voltage per phase. Okay? And in the computation of the percent voltage regulation, like what I said, it should be the no load voltage minus the full load voltage over the full load voltage times 100%. And that's the percent voltage regulation. For this morning, I just presented the way and how we brought out the parameters in the computation of the percent voltage regulation. Okay, that's it, guys. This is Professor David J. Delos Reyes. Good morning from Los Angeles.